Okay, I guess we'll get started. So yeah, welcome everyone to the last workshop of the year. Woo! I'm Jason. I'm an event lead. It's also my last workshop, so that's exciting too. The topic is adversarial machine learning, and this is a beginner-friendly intro to this topic. So there's actually not really going to be any like crazy math or anything. It's just super informative, but it's not anything technically insane. So yeah, I hope you enjoyed. The check-in code's in the top corner if you haven't checked in yet. And that's the website to check in. So yeah, I'll give you a moment to do that. Okay. Any questions before we begin? Okay. Yeah, so machine learning, right? As I'm sure you all are aware, it's kind of becoming very popular these days. And it's trying to find its way into like these quote unquote safety critical applications. And so what does that mean, right? So an example, a very popular example is autonomous driving, right? So in autonomous driving, like you have this car and it has this camera system or whatever sensor system, and it takes input regarding its environment and it tries to like drive the car for you, right? Hopefully safely and in a way that you're going to make it to your destination in one piece, right? So that's an example of safety critical where their safety is really important and there also happens to be ML involved in the pipeline somewhere. And so I'm not going to require you to know too much about neural networks, but we'll kind of give a brief review of what they are. So basically, in the field of AI, there's something called machine learning, and then in there's something called deep learning, and finally there's neural networks, right? So it's important to realize, if you aren't familiar yet, that neural networks does not equal AI, right? It's like a very small tool within a very larger field. It's a very popular tool, but it's not everything. But it's going to be the topic of today. We will be focusing specifically on neural networks and where they can go wrong, right? So to recap, there's a bunch of things you can do with neural networks, but at the end of the day, they are just functions that take in some input and output something, right? So here you see an example of what we call image classification. It takes in an image of a dog, and then it says, hey, this is a dog, right? Another popular task for like computer vision stuff is object detection. So that's where you take in an image, and instead of just saying what it is, you also kind of draw a bounding box on the image to show where exactly it is. And you can have like multiple stuff in the multiple things that are detected in the image too. Any questions so far? All right. So yeah, that was kind of a brief review of neural networks. There's obviously some problems in neural networks. They aren't perfect. They're meant to model data. They're meant to produce these models of the world, of these data sets that we have. But they need training data in order to actually like work, right? They need to be trained. They're trained using something called gradient descent. You don't need to know how that works, but you do need to be aware that that's a thing. And there's like all sorts of problems related to gradient descent. We also won't get too much into that. We'll hint at it a bit later on. But one big thing that you need to know is that neural networks can be wrong. They aren't perfect. They're based on data, and because of that, there's like room for error, right? And so, for example, here, like, you know, this is what's called a misclassification. And usually like a measurement of how good a neural network is accuracy, right? So a big accuracy is good, small accuracy is bad. And if you want more on all this, you can take 151B or some other deep learning course or resources online, right? Ideally, we want accurate models, right? We want correctness, right? That's nice to have. But is it just enough to be accurate, right? So let's consider a scenario where, so that's Bob or Jason, I don't know, whoever you want it to be. It could also be, you know, I don't know, David or whatever, but we'll just say it's Bob for now. And so Bob's actually not driving the car. This is like the only illustration I could find. This is an autonomous vehicle, as you can tell from the Tesla logo. And so for autonomous vehicles, you have like some neural network on board and maybe some big camera system or other sensor system. And let's say that Bob really loves Tesla and he really trusts his car, right? So he decides to go to sleep and not really pay attention to the road, right? So he's in his autonomous vehicle, it's driving on the road, and well, he says, yeah, you know, this is probably, I don't really know how this works, but I trust it, so I'm gonna trust my life into this car's hand. And let's say the car comes to a stop sign, and ideally we would want the car to stop. Maybe there's like traffic coming from, you know, the side. But let's say someone, a third party, someone very malicious, maybe like a hacker or like someone who just, I don't know, wants to mess with people, comes in and messes up the stop sign a little bit, maybe add some words, maybe put some stickers on it or some other distracting imagery on the stop sign. And they do it in a way that actually tries to trick the vision system on board, right? So in this case, the neural network is going to think that it's a speed limit sign instead, somehow, right? We'll get into how it does that. And so that's ends in an unfortunate accident, and we're kind of left wondering, like, how did this actually happen, right? And so that was an example of what we call adversarial attacks. Basically, the overall idea is that you first take something that you know the model is going to do correct, right? So in this case, we have like the stop sign minus like all distracting stuff, right? That should be very easy to classify. Like it's very obvious to you that's a stop sign. But an attack is going to change it somehow, right? Like add some stickers or like change the color or do something funky with it so that now the model is going to predict it wrong, right? To us humans, we can obviously tell that, you know, the thing was still a stop sign, but to a neural network, the goal is to actually fool it some way. And the technical term for like an image that accomplishes this is called an adversarial example. Right, so an example, we had the original image and then our adversarial example. Any questions so far? Okay. So I'm going to play a short video to show you that example that I just showed you is actually like that's a real thing. Like someone actually went out and did this exact thing.
First impressions mean a lot. Like when.
All right, let's skip the ad.
And of course, in a dynamic environment, we can see when we drive a car towards this sign, on the left-hand side, it's one of the perturbed sign we showed in the last slides. And on the right-hand side, it's a control experiment with a vanilla stop sign. And we can see from the caption that when the car driving towards this sign, it's consistently misrecognize the sign itself as a speed limit sign, but the control experiment can correctly recognize it. So this shows how severe or dangerous it could be, even with such simple like planar road sign as adversarial object in real world.
Yeah, so that just shows you that I didn't make that up. Like people are actually working on these kinds of problems, and it's actually definitely very possible for these kinds of attacks to happen in the real world. Okay. So the next couple of slides are just some examples of like real work people have been doing in adversarial attacks, right? So what we just saw was an example of from this paper. Basically, they cut up a bunch of patches and they put it on a stop sign in a way that they could actually get the neural network to believe it's something else, right? In this case, like a speed limit sign. And here's kind of like the diagram that showed how they did it. Basically, in the top right corner, you see the ultimate classification is a speed sign. There's different kinds of adversarial attacks. So in this case, we have object detection. And the goal here is to add a bunch of like fruits onto a stop sign or other objects, such that the stop sign is actually not even detected anymore. In the far left, so each of these are kind of frames in a video feed. And the point here is that in the far left, you see like, oh, there's like a stop sign detected. But for most of the frames, it's actually not detected, right? So in most cases, you can actually generate a very successful attack, at least in this example. And there's different kinds of ways that you can actually physically attack things. So instead of just attacking the physical object, you can also like attack the camera itself. Here they created like a translucent patch, and then they put it over the camera such that it basically accomplishes the same thing, right? Like it messes up the vision a little bit so that now all stop signs are not detected anymore. So your car is just constantly going now, it never stops. And so the common theme you might have seen so far with these examples is that they're like super obvious, right? Like it's really obvious that something has been changed physically in these stop signs, right? And so realistically, like, I mean, if you're on a highway, you can't really do anything because you're going like 70 miles an hour, right? You're not just gonna hop out of your car and change it in the middle of the road. But if you're like in a residential area, then, you know, someone could just look at this and then, you know, take off the sticker or whatever. But not all adversarial attacks are super obvious. And this is actually where really dangerous attacks come into play. So you can kind of see on the top side here, there's actually two images that look like they're the same thing, but actually they're really similar, but slightly different, right? And I don't know if you can see it, but like, for example, the McDonald's logo on the bottom right of each image is actually on the right side, it's a little bit corrupted. So basically in this attack, what they were able to do is create a poster, a real world poster that was really similar to the original one, but actually caused the vehicle to basically go crazy with its steering and, you know, potentially crash. I think they were going like really slow, like 10 miles per hour, but it showed that you can actually modify like the vehicle controls using these kinds of examples. And it doesn't have to be like super obvious, right? So, and the other thing is that, yeah, Ishan.
Do we know what the car thought it saw when it saw that sign?
So from what I know, they the attack was on I'm not sure about the classification, but like the ultimate output of like the steering angle and like velocity, those were actually changed based on like this example.
Yeah, I was wondering about the classification.
Yeah, I'm not sure about the classification, but yeah. Okay. So in general, like we kind of view these more discrete examples as a stronger attack, right? Because they're harder to detect, right? Like if you were driving on the road and you saw that sign, you know, driving at like 30 miles per hour, you don't have enough time to actually like realize that it's something's a little wrong with it, right? And even when you show that, if I didn't tell you that it was an adversarial example, you'd probably say it's like a normal image, you know, minus the weird McDonald's symbol, right? So these are really dangerous, and they can be very subtle and hard to detect. So moving over to like the digital world and thinking about how these are actually constructed, right? So like we have an original image, in this case, a bus, and most common adversarial examples add something called a perturbation to the image. So we're actually perturbing the pixel values a little bit. And this produces a, if you have a very strong attack, right, a very discrete adversarial example, this produces an image that is really similar to the original one, but still slightly different, right? So, you know, your pixel value could change from like 0.1 to 0.11, right? And it'll be a different image, but like visually, it'll pretty much look the same to a human. But to a neural network, because of how they are designed mathematically, this can actually lead to a very big difference in like what the prediction ultimately becomes. So some more technical jargon. So usually in these kinds of settings, we don't just let the attacker, we don't just assume the attacker can just change something however much they want, right? And realistically, like a good attacker would want to be very discrete, right? So we define something called a perturbation budget, which just says there's a limit on how much you can change the image. So like if you have a large perturbation budget, that means you can change the image a lot, right? And so I'm just going to answer the question here is that it becomes easier to find a successful attack because of the fact that you can look through more images. You can look through more possible images. In terms of discreteness, it may result in a less discrete image because you're changing it more and more, right? So, you know, maybe that bus becomes even more fuzzier, and so it might be a little more suspicious. But if you had a small perturbation budget, then, you know, that's going to make it look more similar to the original image if you have a successful attack. Any questions on anything? Okay. Great. So here's where, so this is probably the most technical part of the whole slide. This is where we actually, and there's also a code example with this. This is where I actually learned how to generate an actual attack. And we'll do this in the browser, and all of you can follow along, and there's like an activity involved too. But just to introduce it first. So one really popular attack that's out there right now is called PGD. PGD stands for projected gradient descent. The term PGD is actually in math, it's more broadly used as just a general algorithm, but in the context of adversarial machine learning, it refers to this, it's utilized for these kinds of attacks. There's some math in here, it's not too crazy. I won't show it, but basically, if you know what gradient descent is, it's just a variant of that. So it's just a little bit of calculus. Yeah, I will move to the next slide. So just going over like how PGD works at a high level, right? So first, you're going to define something called a loss function. If you don't know what a loss function is in machine learning, don't worry. All you need to know is that, you know, here I have a toy example of loss function. It's just a mathematical function, like something that has like terms and coefficients and stuff. But it's defined in a way so that like a higher loss value, like a higher value for this function corresponds to like a worse prediction, right? And so ideally, remember we said we want more accurate models, right? That would correspond to a very low loss, right? A very high loss is really bad because that means you're like misclassifying everything. Yeah.
Is this loss function, is it defined as a function of weights or?
Yeah, so that's the next thing. So when you're training a neural network, right, you're going to be changing the parameters of the network, and you're going to assume that the images are, you know, unchanged. In this case, we actually do something different. So in the horizontal plane or like the input plane, these are actually image pixel values, right? So visually, you can imagine like a whole bunch of buses, right? If we're in the area for buses locally, and moving along the space on the bottom plane is going to go to very slightly different variations of this bus. And so before I go there, so like what's the goal of an adversarial example is to basically say like, hey, let's find a bus that's like really similar, like it's in this neighborhood somewhere. So it's really, it looks similar, but we're trying to get it to mispredict. We're trying to get the neural network to mispredict, right? So we want to move in a direction that's going to have a very high loss. And just to throw in that, yes, so in these settings, we usually have a perturbation budget. In this case, I drew it as like a blue circle. that basically means that like we limit what the attacker can change the image to. So it has to stay within the circle. And then I just I wrote out the actual algorithm, but I'll go through it step by step. So basically we did first step, we define a loss function. And so the second step is that we actually need to like pick a starting point, right? And so we have this original image, which is a bus in this example. And the first step is going to actually be to not start at the original image, but actually start a little bit around the original image. We're going to add a little bit of random noise to the image so that, you know, maybe we don't start at the exact bottom, but we start a little bit off of it, right? And we'll get to why we do that in a bit. And then basically what we do is we just, we start taking steps, hopefully in a direction that's going to increase the loss value, right? So we're basically repeating two steps. One is to like check the prediction. Did we mispredict? If so, we've succeeded, right? We've got a misprediction, we've fooled a neural network, right? And then we can stop there. But if we haven't found a misprediction yet, then we need to keep searching, right? And so how do we actually take a step? Again, that's like the more calculus part of it, but basically if you look at the shape of here, right, you want to go in a direction of like, that's going up, right? So basically you go in a direction that's going to increase your loss function value the most. And then you just repeat those. So like, for example, we, you know, calculate a step and then we move the image, right? So after one iteration, it looks very similar because, I mean, we haven't changed it too much. But now our loss value is actually a little bit higher than where we were before. And we just keep doing that. So we calculate a direction, move the image, we keep checking the prediction. And finally, we see that we have a misprediction, right? For example, now we finally got to the ostrich part, right? Maybe like our loss is like super high, it's high enough where we're able to switch, right? Are there any questions so far? Yes.
So like since it's trying to find like when the prediction changes, like is the purpose of like this like PGD to find like the boundaries of like the scope of how good the prediction like the boundary of when it actually gets wrong?
Yeah, so in a way, yes. The actual boundary is really hard to find, but you can sort of find, so like if you imagine like, actually drew it on the next animation, let's say that was the boundary, right? Like that was the true boundary between like ostrich and bus, right? You actually don't know ahead of time that that is a boundary, and to actually find that is like really difficult again. What PGD can do is sort of say, let's find like an over approximation of that boundary, or like, let's look for an upper bound on that boundary, right? So, you know, again, like you don't know the green line that here exists, but you can say like, it's at least behind this red dot, right? So like, yeah, so PGD can give you an upper bound on the boundary, basically. That's a good observation. Any more questions? Okay. Oh, yeah.
So the perturbation budget is based on how far the image is in some sense. So would it just be like changes in pixel count? Or like, is there a better measure which is like closer to human similarity?
Yeah, so this is so there's different ways you can define the perturbation budget. If you just do a circle like this, then it's what we would call like an LP norm. And then you can have different values of P. But you can also have transformations that aren't like LP norms, like you can have like rotations and like all these and like blurring or like yeah, like different color shifts. And those can also produce attacks, but aren't like they don't look like a circle. They look something like really weird. And that's like an actual, it's an active area of research right now. So, but yeah, like if you go into like Google Scholar, like the most popular way to define it is just like an LP norm. It's just like a circle, basically. Okay, any more questions? Okay. So yeah, so basically, again, there's this hidden line, this green line, where we sort of cross the decision boundary. And we don't know where it is, but the goal of PGD is to, at some point, cross over it. And as long as we're in the other side of it, we succeeded, right? And this loss function in this case, like it can have like, other decision boundaries, like maybe if it went over there, it would go to zebras. If it went towards like out of the screen, it would go to like some other region like frogs, right? But again, like it sort of depends on where your initial starting point is, right? So like we started on sort of the left side, and that's sort of why we moved over here into this ostrich region, right? And so here's like a question for you all. Why do you think we actually add this random noise at the start to like our original image? Like, why do we not set it to the original image all the time? Yeah.
I would guess that if we happen to be at some minimum cell point that we added it down to as well. But I'm not sure why necessarily the derivative with respect to that image values would be at a cell point for them.
Okay. Any other thoughts? So yeah, so I think David was on the right track. Basically, it kind of goes back to this point here, right? Like, depending on where you start, you can sort of end up in a different region. And this is obviously a really like toy example, but you can imagine like real loss functions. They're like super complicated. They have like really weird landscapes, right? That red dot can get stuck in some places, and it can be really hard to like actually be able to cross any boundary, right? And so what a random adding like a random value does is it allows us to kind of jump to a different point, right? So maybe instead of starting like starting here, right? Let's say maybe that was like a really bad spot to start. Like adding like a random point would, allow it to jump to a different point, which could then, push it to a different decision boundary like more easily, right? So the overall idea is that like it's trying to help exploration, right? Because of the fact that the way PGD works and how these functions are designed, it can get stuck. It can be really hard to actually like cross a boundary. So this random thing kind of helps with exploration a little bit. Okay. Yeah.
These perturbations don't look at all like the direction that you would expect, but they don't resemble at all adding some ostrich image to the original image. It just looks like most.
Yeah, so yeah, like I mean, and that goes back to like the what it means to have a strong attack, right? It looks super similar to the original image, right? It's obviously not an ostrich, but in reality, we did change the image just very discreetly. Yeah. Okay, so here's like the interactive portion. If you brought a laptop or a phone, that could work too. Just go to that URL at the bottom, acmurl.com/adversarial-ml-code. And it should take you to a Jupyter Notebook or like a collab notebook. And basically what we're going to do once you pull that up is run PGD and kind of play around with it and see how like changing different parameters of PGD is going to affect your attack. So I'll give you a few minutes to open up the link. Okay. Does anyone else need the link, or are we all good? Okay. I'm going to open the link too, so I can follow along. Move that out of the way. The high level idea of this notebook is that we have this pre-trained model, and it's trained on this data set called CFAR10. So CFAR10, let's see, this is not a good image. Yeah, so CFAR10 looks like this, right? Like you have 10 different categories, right? Airplane, automobile, etc. And you have like a bunch of images in this data set. And basically, I just found like a model, and that was already trained, apparently by DeepMind. So we're going to show that DeepMind trained models aren't very secure. And we're just going to basically attack it and watch it blow up. So if you don't know how to use Colab, there's these like little play buttons next to here. And also, if you want to save your own copy, you could go to File and then save a copy in your drive. So you can come back to it later if you want. But to actually run a code, there's these little play buttons. You click Run Anyway. And it might take a little bit to load some of this stuff at the start, but once you do that, it should be pretty smooth. You don't need to fully understand everything, and especially if you're not familiar with Python, but the actual changes you'll make are like pretty straightforward. So we'll walk through that too. But basically the idea is that like we load this data set, and that might take a while too, because it has to download the data. And then, yeah, so a couple seconds. Yeah, so we're loading CFAR10, and then some other code here is just performing some preparation for the data. And then once that happens, we can load our model, our DeepMind CFAR10 model. And then here we're actually like we're actually going to use the model, right? So here like we have an image of an airplane, and we know the ground truth. Like we know it really is an airplane, right? That's what our data set tells us. And in the next cell, we're going to check what our model says. And our model prediction is correct. It's an airplane, right? If you want to change the image, just change this line I equals 10 here to like some other number. It's like 37. So here's like an automobile, and then basically just rerun a small prediction. And oh no, our model has produced an incorrect prediction, right? So this is kind of proof that, yeah, like the model isn't perfect. It's really good. It predicts correctly in most cases, but sometimes it gets things wrong. And also like truck is that's pretty close. I probably would have said truck at first, but anyways, so yeah, you just play around with this, look at different images, and then I'm gonna stick with the number 10 image if you want to follow along, but in part 2 is where we actually conduct the attack, right? So the 2 main points that you're going to modify are basically these variables. These are your PGD variables. And if you want to change the image, again, like you could change the I variable. And that's all you really need to change in this notebook. Unless you want to add like more fancy stuff. But okay. So this last cell here is pretty much PGD. If you cross-reference like hold on, to cross-reference like this algorithm I posted here. You can go back to it later. I'll send the slides and everything, recording. But basically, it's like basically outlines what's going on here. So I'll just kind of briefly go over it again. But basically, we take our original image and then we define our loss function. You don't need to understand what all that jargon is, but we have a loss function. And then we're actually, again, we're adding our random perturbation as our starting point, right? So we're helping exploration a little bit. And then basically our value K is going to be a parameter that's going to be like the number of iterations we're going to run PGD. So it's the number of steps that we're actually taking in total, right? Or the maximum number. So basically, for each iteration, we're going to check, hey, did this prediction actually change? Did we successfully attack the model? If so, we just stop, right? If not, then we need to actually take a step in a direction that's going to improve our loss, or yeah, increase our loss, right? Because that's what we want to do. And then we just take the step. So we're actually changing. Adversarial is going to hold our image, which we hope at the end of this is going to be our adversarial example. So it's kind of like we're changing it each iteration. We're adding on to it more and more. And yeah, this just runs like K times, and it keeps stepping. And then at the end, we just check if we found anything. And if we have, then this last prediction is going to be different from the correct one. And if we haven't, then it's going to say attack failed. Any questions about the code so far? Okay, so what you're going to do is this activity, and also feel free to work with people next to you. But basically, each step is going to try to hopefully teach you something or allow you to understand something better. So the first thing to do is just, if you haven't done so, just explore different images, like change the I variable and see, like, just get a feel for the data set. And then the second one is going to be a little bit of a challenge. And so I'll start that now. So basically what you're going to do is you're going to go up to here and you're going to change this to 4, I equals 4. So you should see like a frog image. And basically what happens is that it's a correct prediction. So it's eligible for an attack. And what you're going to note is that when you actually run the attack, it actually fails. And so it fails because, with the amount of steps that we specified and also other parameters, it wasn't able to find a successful example, within 10 steps. Maybe it needed more steps. Maybe we need to change the step size. There might be some things you can change, but the challenge is to actually change only K and step size so that you can actually get this thing to succeed. And don't change the radius. So we're actually like trying to conduct a real attack, because in real world, you're not going to change the radius. So K and step size. Your goal is to get this to actually change the last prediction. So I'll give you maybe until 6:50, and yeah, feel free to collaborate or whatever. And also, I'll give you a hint. So if you look at, I'm also printing the loss here, and you'll note that it's increasing, right? Which for an attacker is a good thing. You want the loss to be big and bad, right? Pay attention to how the loss changes, and that will help you succeed with your attack.
know the takeaway position, like how some people compare those to take it on so say actually you have a passport, so you don't have a passport. If I show you still your passport, they'll say, oh, I have it. So if I want my face, then they go to the internet. They'll say, oh, but if you will say, oh, it's me. Because after you take with official documents, they're now trying to zoom out. The classifier was that you can't recognize whose face that is because it's where it's just faces. So you have to separate that out as a separate person. Well, that one's possibly well, okay. Well, okay, true. But still take that. Yes, except that we might be able to use that's the real stuff. That's what I mentioned. So alternatively, you could make it so that you can just edit the image. So that's a bit that image that does. If you can do that as well. But to possibly not precise, but always still manage most of the stuff.
That's DCTF with AI. Yeah.
That's a lot of tests.
I'm trying to stop it.
You can see it. Well, it's okay, it's a notebook, so it's block by block, so you can put block as part of it. Yeah.
Jason,
Mhm.
change speed or no?
You only need to change K and step size. I would recommend staying with those two.
Okay. But it's
Just a random value, very beginning.
Oh, so some cost.
yeah.
Okay, so we're gonna move on now. Did anyone actually succeed with the attack? Did anyone succeed with the attack? We got 2 successes.
He did, I just copied it.
Oh, yeah, okay. Do you want to share like what you changed?
Yeah, I just upped K to 100 because I mean, originally I upped K to 1,000. Just why not have more Ks? But 100 was all necessary, and then step size was 002.
002. There we go. Yeah. So on the 24th step, we have a change to bird. Cool. Yeah, that's awesome. Congrats.
Flag captured.
So yeah, so if you're familiar with deep learning, or if you want to become more familiar, this is very similar to like what we do with like what's called hyperparameter tuning with gradient descent, right? It could be really finicky to like change all these parameters to get something to be successful. And that's kind of like the lesson that I was trying to teach you here with this this thing. It's like if you have all these parameters, and to actually succeed with an attack, it can actually take some time, like manually like figuring out like, okay, what's the right K, what's the right subsize I need to use, etc. So you can complete the rest, the 3rd step on your own time. Basically, it's to just play around with the radius. Let's see. Yeah, well, I think we'll. Let's see, what should we do? Yeah, so I guess we can like go through. So like what change impacts the execution time here? Like which parameter makes it slower or faster? Like what's the main parameter that we're changing here to affect that? Yeah. Yeah, it would be the number of steps that you're taking, right? So your algorithm would be pretty much O of K, right? It's proportional to the number of steps that you're taking. Is there a way that we can improve this algorithm to maybe make it easier to find adversarial examples? Yeah. In terms of like the actual algorithm itself, are there ways so we can extend it, or yeah, you add some more loops or stuff like that, and or change the parameters with that? Yeah.
As the like loss increases, maybe make the step size like smaller or bigger. I'm not sure one. It's more like basically change the step size so that like it becomes more like accurate and the loss.
Yeah. So yeah, exactly. Like that's one way you could do it. You can have what's called like in gradient descent, that would be called like a learning rate schedule. In PGD, I don't know, we would just say a schedule for your step size. But yeah, you can like vary like the step size. Ideally, you'd probably want to make it smaller as you go on with as the number of steps increases, or like as you go further, like as you enter later in iterations, you want like a smaller step size. Any other things we could do? So like one other idea, if you remember back to like our like random initialization thing, right? I mentioned like the reason why we have like random noise is to help exploration, right? And exploration is good because it helps us actually find these successful examples, right? So one idea is just to keep rerunning the random initialization, right? So have like a big overall outer loop that just reruns PGD on a different initialization, right? So you're starting at a different point, try again. If that fails, rerun initialization to a different random starting point, try again, and just keep doing that until you find a successful example, right? Does that make sense, everyone? Like that's Another possibility. Like, what would be the cost of that in terms of runtime? Yeah.
So you can also bias the story to specific other class. Okay, so rather than just simply creating the loss.
Yeah, so yeah, David asked about like perturbing the image towards like a specific class. You can totally do that. And actually, the term for that is called a targeted attack. So what we're doing in this notebook is called untargeted, which means we don't care what class it ends up as long as it changes, we've succeeded. But if you wanted to change it to something specific, that would be called a target attack. And then you would have to make some modifications to algorithm to do that. Okay, I'm gonna move on for the sake of time. So we just explored like how to actually attack these models. And basically, we kind of showed like accuracy isn't like enough, right? Like if we want our models to be safe to these kinds of attacks, we also need a property called robustness. And robustness just means if your model is robust, that means it's harder for these attacks to succeed, which is what we want, right? Any questions so far? Right, so like if we had modified our car so that was more robust, then maybe you would have thought it was a stop sign instead, right? But like this is kind of always like it's kind of like a two-sided game, right? Like so maybe your attacker, maybe you celebrate because it was successful, but maybe your attacker comes back and that's another sticker, and then now it changes to something else, and then you kind of fail again, right? So it's like constantly like you're always. It's like attacker versus defender, right? It's like a game, right? And so I'll kind of just blast through these last few slides. They're mostly informational if you want to go through and learn more about this. But the other two aspects of this field are, the first one is verification. So I'm just going to summarize the slide. Basically, verification is saying, like, how can we actually know, like, in advance that our car would be, okay with this, but like not okay with this, right? Naively, you would probably just like run through every possible perturbation and see if it like succeeds or not, right? But that's like not very good. That's brute force, basically, right? And so verification is saying that, look, you don't have to explore every possible attack, right? Using some clever math, you can actually verify much more quickly whether or not your attack would succeed or not, right? And there's different kinds of approaches to verifications, and the main point is that with verification, there's this big trade-off between how terribly slow your algorithm is, and most are pretty intensive, versus like how exact your verification is. And by exact, I mean like, what can you actually verify, right? Maybe you can verify like, at least, images this far away are going to be safe, right? Rather than saying like, what's like the, exact like boundary of safety here, right? Yes.
What exactly does it mean to be verified? So that means if you perturb it, it won't change. But like, what if it's already like a perturbed image? If it's like close to some decision boundary already, and then how do you say this?
Yeah, so verification is always on the original image. So it's with respect to the original image. So basically you're saying like, with respect to this image, like if we perturbed it and any way that we would perturb it within some radius, like it's not going to change the prediction. Okay, and then the last thing that you need to know is defense, right? So it's not just enough to like be able to attack it and then throw our hands up and then, or even just to like verify it, right? And then maybe our model we realize is terrible, right? It's like our verification told us it's like super unsafe, right? Okay, what do we do about that? Like how do we improve our models like robustness? That's where defense comes in. And you know, there's a lot of approaches to defense in literature, and you could spend like a bunch of time looking into them. Most of them, their goal is to increase robustness, which means just make it harder for the adversarial attacker to succeed. And most of these methods basically are modifications to your training time. So when you're actually training a model, you're not just training it to be more accurate, which is what like standard or typical training looks like. You want to train for accuracy, but now you're training for accuracy and robustness, right? And if you're familiar with machine learning, that can look like adding a specific loss term, additional loss term in your loss function, right? But the big takeaway is that like those kinds of methods, they only encourage robustness, just like how normal training only encourages accuracy, right? Like it'd be really nice to say like, I want a model that has like this much robustness, right? But that's the same difficulty as saying, I want a model that has like 100% accuracy, right? Like, if we could do that, then like the world, like AI's problems would be solved, right? And we have like perfect models and perfectly robust stuff, right? But this is actually a really active area of research. It's also very saturated. So another big takeaway is that there's a lot of work going on in this area. It's like super active, and it's AI is already oversaturated, but like this area is also becoming very saturated. And so yeah, like here are some active problems. Basically, one big thing is that we just need to know how we can train models that are both accurate and robust. Currently, we don't really like, we're getting there. Like we have some ideas, we have some results, but really like overall, we don't know like how to do this, right? So sometimes you can have a really accurate model, but like robustness is pretty terrible. Sometimes you have like a really robust model, but like accuracy is terrible. We need a way where we can do both, right? Like a very accurate model and a very robust model. Yeah, so like if you're interested in that, maybe you can look more into that. If you're really interested in this topic, I would recommend following up with this paper. It's a very gentle introduction where like you only really need to know like some algebra, and it's called IBP, it's by DeepMind. But actually, I think within this field, it's one of the more accessible papers. So look at that paper if you're more interested. Also, you can always go to Google Scholar for more info. So yeah, so like these are kind of the 3 pillars of adversarial robustness. These are the 3 terms you should remember: attack, verification, and defense. And yeah, that's all. Thanks for coming. If you have any more questions, just let me know. Cool. Yeah, any questions? Yes.
That's like, do you explain the trade-off between like complexity and attacks?
Oh, okay, yeah. So this is, let's see. Yes, I can. So let me go back to that slide. So there's sort of 2 different kinds of verification. One is going to say like, so I have like these 2 problems, right? Like one is we want to verify like, for like a given perturbation budget, is any attack going to succeed, right? Yes or no is basically this kind of verification. It's called complete verification. And this is like what we want, right? We just want a solid yes or no. Is this safe or not, right? Unfortunately, that's like a really hard problem. It's NP complete, which means it's possible to compute, but it takes a really long time. And for really large neural networks, it's actually, you'll run out of time, basically. And so like what we mean by like trading off complexity and exactness is saying like, instead of giving me a solid yes or no, you could give me like something that's a little more fuzzy, right? So for example, in complete verification, we could say a yes or I'm not sure, right? Like not a solid no, but like maybe. Or like, for example, if you want to find a specific number verification, for example, like we talked about like the decision boundary and like where it exactly is, right? Finding that was like really hard, right? So maybe instead of finding exactly where it is, we talked about like finding like an over approximation, right? But how close that approximation is to the real boundary is what exactness means, right? Like the closer it is, the better approximation it is, right? But also the harder it is to compute. So that's what we mean by trading off like complexity versus exactness.
So like less complexity. Like if it's a similar approximation that's like it's less exact.
Yeah, in general, it would be like a faster algorithm, but your like answer would probably have like, it would be less close to the real answer. Any more questions? See if there's any Zoom things. Oh, no. Okay, so if there's no questions, feel free to hit me up on Discord if you think of any later. There's also pizza in the back. Please eat that. it's in the way back. But yeah, thanks for coming. So yeah, the workshop's over.
No.
Huh?
So the word budget here.
It'll stop by itself.
There's something in CS called, well, we usually look at algorithms in many ways. Main way we look at them is through how long it takes and how much memory it takes. And we follow, space and time, time and space complexity.